Imagine trying to protect something incredibly delicate and precious, something that even looking at it directly would change or destroy it. In the realm of quantum computing, our precious items are qubits, and they are incredibly fragile, prone to making mistakes due to noise or interference. So, how do we catch these errors without disturbing the very quantum information we are trying to save? Syndrome measurement identifies specific qubit errors by detecting changes in the entanglement or correlations between qubits, without ever directly observing the state of the data qubits themselves. It provides a distinct signature, or syndrome, that points to the exact type and location of an error. The core mechanism relies on a clever interplay of entanglement and measurement. We introduce special helper qubits, called ancilla qubits, which are initially prepared in a known state, often the zero state. These ancilla qubits are then entangled with the data qubits using carefully chosen quantum gates, most notably controlled NOT gates. These gates are designed so that if an error, such as a bit flip or a phase flip, has occurred on a data qubit, this error information is subtly transferred into the ancilla qubit state without altering the data qubit's computational basis state. For instance, a bit flip on a data qubit might cause a specific change in the ancilla's state, while a phase flip would cause a different, but equally specific, change. This differential response allows us to diagnose the error type. The process begins by logically grouping our data qubits and associating them with these dedicated ancilla qubits. Then, a sequence of quantum gates, primarily controlled NOT operations, is applied between the data qubits and their respective ancillas. This step, often referred to as syndrome extraction, creates a unique entangled state. Once this entanglement is established, we measure only the ancilla qubits. The outcome of these ancilla measurements gives us the syndrome. For example, if a group of ancillas returns a 000 measurement, it might indicate no error, but a 100 measurement might specifically signal a bit flip on the first data qubit. This measured syndrome is then used to deduce which error occurred and where, allowing for a targeted correction. This elegant method is the cornerstone of many quantum error correction codes, particularly those known as stabilizer codes. Stabilizer codes provide a formal mathematical framework for designing these entanglement operations and mapping the measurement outcomes to precise error types. A key aspect of why this indirect approach is so crucial relates to the no-cloning theorem of quantum mechanics, which states that we cannot perfectly copy an unknown quantum state. By using ancilla qubits and syndrome measurements, we gain information about the error without ever needing to copy or directly inspect the delicate quantum information itself, thus preserving the original quantum state for computation. Ultimately, syndrome measurement is a brilliant stratagem that enables us to maintain the integrity of fragile quantum information. By indirectly pinpointing the exact nature and location of qubit errors, it allows for their correction, paving the way for the development of robust, fault-tolerant quantum computers that can tackle some of the world's most challenging computational problems without succumbing to the constant threat of noise and decoherence.
If quantum tech fascinates you, like, subscribe, and keep exploring with us.